Well, hi. Welcome to today's lecture on basic architectural acoustics. Today we are going to talk about some of the things that happen to sound as it travels through a medium or encounters obstacles. So we're going to discuss the first important thing, that is reflections. Then we're going to talk about the focusing of sound, the scattering of sound or diffusion. We are also going to talk about the diffraction of sound, and at last we're going to talk about the refraction of sound. We are going to start off with talking about reflections. To understand reflections, we approximate the sound wave, which is actually a wave, as a ray. You have to note that a ray is just an approximation. It's not exactly how sound works. We just approximate sound waves as a ray for convenience and ease of explaining concepts. So reflections. So on a flat ground, or on a flat surface, the angle of incidence of the sound is equal to the angle of reflection of the sound. On open ground, the sound never comes back to the speaker because the sound always moves outwards. This is how reflections work on open ground. Now we're going to discuss the focusing of sound, and we're going to discuss the scattering of sound or the diffusion of sound. So first, before we talk about focusing and scattering, we'll talk about echo. An echo is a strong reflection that comes back to the listener after 100 milliseconds after the original sound has been produced by the same listener. So suppose S is the source of the sound and L is the listener. S produces a sound. The sound travels all the way, hits the wall and reflects back to the listener, L. If the time taken for this round trip going hitting the wall and coming back is more than 100 milliseconds, you will hear it as an echo. So if it is less than 100 milliseconds, what the ear does is it integrates both the sounds and you don't hear it as two distinct sounds. That's why you cannot hear an echo if the distance between you and the wall is not too far enough. I think if I remember correctly, you need at least 16 or 17 meters of distance from a flat wall to hear an echo. There's one more thing called flutter echoes. This is when you have two parallel walls and the source produces the sound. The sound hits the wall and reaches the listener, who is in the middle of the room, and again it hits the other wall. It bounces back and forth between the walls. After each bounce, the sound loses a little bit of energy. Hence why I have reduced the thicknesses of the arrows. The thing is, a flutter echo, if you clap once, you're going to hear something like that. So that is a flutter echo. So now what is focusing of sound? Focusing of sound happens when you have concave surfaces. This is similar to what you studied in optics. Because we are approximating sound to be a ray, it behaves like some of the basic optics where we treat electromagnetic waves as rays. Concave surfaces tend to focus sound. Here you can see the sound hitting a concave surface and focusing at a particular point. At that point, the sound level will be very high. That is called like a hotspot. So now we'll talk about diffusion of sound. When sound hits a convex surface, the sound is dispersed in different directions. This makes sure that there is no strong reflection coming back in the same direction. The sound is turned away in many different directions, so the strength reduces in each direction the sound is going. So convex surfaces tend to diffuse sound. Please remember that. So any polycylindrical surface that you place in your room or home theater or recording studio, that can act as a diffuser. This is a simple form of a diffuser. A convex diffuser is a simple form of a diffuser. So next we'll look at another way sound can be diffused. When sound waves hit a rough or jagged surface, they tend to bounce off in all different directions, in all different random directions, and this causes the diffusion of sound. Once again, here you don't have strong reflections. Strong reflections only occur when there is a specular reflection. I'll show you what a specular reflection is. So specular reflection is a strong reflection. The sound hits the flat surface and bounces off. Angle of incidence equal to angle of reflection, and the reflection from a flat surface is also known as a specular reflection, because the sound doesn't diffuse, the sound doesn't go in many different directions and lose its intensity. The sound intensity remains almost the same. This is called a specular reflection. Usually specular reflections are strong reflections. Diffuse reflections are weak reflections. Particularly in rooms, we would like to mostly have diffuse reflections, so that the late reflections are not disturbing the original sound. We'll talk more about this in the room acoustics chapter. Okay, now let's come to diffraction of sound. Diffraction is the property of sound wherein when sound goes through a slit, it tends to bend around the corners of the slit. This is known as diffraction. Diffraction is especially large for low frequencies. Diffraction is low for high frequencies. At very high frequencies, the sound passes through the slit almost like a bullet passes through a narrow opening. This is the diffraction. Diffraction depends on the frequency. So low frequency, more diffraction; high frequency, less diffraction. Diffraction also depends on the gap of the slit. If the gap of the slit is large, the diffraction is low. If the gap of the slit is small, then the diffraction is high. Also, diffraction happens around obstacles. Suppose this black line here is the ground, and the blue color block is a building in which people live, and the orange color or the cream color wall is a barrier. Sound high frequency sound almost passes in a straight direction with a little bit of diffraction, but however low frequencies, they tend to bend around that upper corner, and they will hit the building and disturb the residents of the building. So low frequencies are always a big problem in acoustics. Low frequencies, I would call them, they're a headache in acoustics. Low frequencies are a headache in architectural acoustics. So this is about diffraction of sound. Then we'll talk about refraction. Refraction, it's very similar to the refraction optics. If you place a pencil in a glass of water, you can see the light bend. It's similar in with sound. As sound passes through media of different density, it tends to bend. That is known as refraction. So here you can see in the first case, there is warm air near the ground and cool air above. This usually happens during the daytime. And what happens is, when you speak, the sound tends to bend upwards and go upwards. But during the night time, the cool air settles on the surface and the warm air rises. This is during the night. So here what happens is, the sound tends to bend downwards when there is cool air on the ground and warm air on top. The reason this is how it is during day and night is this: during the daytime, the sun's rays heat up the ground. The sun's rays heat up the ground, and that's why near the ground there is warm air, and the cool air is above. During the night there is no sun, so the cool air settles down, warm air goes up. As you all know, warm air has a lower density and cool air has a higher density, so therefore this type of bending happens. So when you have warm air on the ground and cool air above, you have refraction upwards. When you have warm air on top and cool air at the bottom, you have refraction downwards. So this is about refraction. This is the end of today's video. In the next video, we're going to go to the exciting parts of architectural acoustics, the real deal, which is room acoustics. So thank you very much for listening. Please do comment, share, like and subscribe, and it is because of subscribers like you that I'm able to make these videos. So please do subscribe and watch my videos. Thank you.